All right, well, I want to introduce you to a really interesting idea. But to inspire it, let's come back to something that's not so interesting, namely finding the length of a vector. Not a big deal. Let's think of it together. Suppose that I have a vector A, and its coordinates are given by A1, A2, A3. So these are the components in the x, the y, and the z direction, understanding that I'm starting at the origin and going out to there. So these are the components of the vector A. Now, what's the length of this vector? Remember, we write it in terms of the absolute value symbol, but it's just the length of that arrow, which would just be the square root of A1 squared plus A2 squared plus A3 squared. And I take the square root. Now, if I were to square both sides of this, that would get rid of the pesky square root, and I would see this. I would see that the length of A squared, or the magnitude of A squared, equals A1 squared plus A2 squared plus A3 squared. And that's sort of a, I don't know, would you really call it a neat formula? It's certainly a formula, and it's sort of straightforward. But what I want to do now is I want to actually generalize this formula. Because really, this is taking a vector sort of A and kind of multiplying the coordinate in the first spot by itself, and then adding it to taking the second coordinate and multiplying it by itself, and then taking the third coordinate and multiplying it by itself. But what if I had two vectors? What if I had a vector B hanging out there, whose components were B1, B2, B3? Then I could somehow combine them in the same way that I combined A with itself by doing, well, a similar thing. Maybe taking the product of the first components and then adding that to the product of the second components, adding that to the product of the third components. And so I would see A1, B1 plus A2, B2 plus A3, B3. And notice that when the B vector is the same as the A vector, I get back the length of A squared. But in other cases, I just get some kind of number that would mean something, I guess. I don't know. But I'm going to give that number a name. I'm going to call this the dot product of these two vectors. And I'm going to denote that with a big, big, fat dot. You've got to make sure that your dot is fat. And this is called the dot product. Something really weird here. Look what we're doing. I'm taking a vector, another vector, and I'm defining a kind of multiplication, a product of these two things, and the answer is not a vector. The answer, in fact, is a number. It's a scalar. It's just the product of the corresponding components all summed up. Okay? And that's what we call the dot product. Is it weird? Yes, but we'll see in a minute this is actually very natural. All right, so if you remember, what I see here is that if I take a vector and dot it with itself, then I get the coordinates or the components squared all added up, which is just the length squared. But more generally, the dot product is defined to be, well, if you take a vector A and B and take their dot product, it's just the product of the corresponding components all summed up. Okay? And when A equals B, you get the length squared. All right, let's do an example. Here are two vectors, A and B, and I want to know what is their dot product. Well, no problem. A dot B. Negative 3 times 2, negative 6, plus 1 times negative 10, negative 10, plus 5 times 4, 20. So here I have 20 minus 10 is 10, minus 6 is 4. So the dot product of these two vectors is the number 4. That's great, except for the big question, what the heck does the dot product mean? What does it mean? What does 4 represent? 4 must mean something with respect to these two vectors, but it's not at all clear what it means. What does 4 represent here? Well, this is a really cool fact. And the way to see what the dot product really represents is to not think about the dot product as it is, but think about something from our distant past. That's right. I want us to journey back right now. Imagine this, those flashback things. And I want us to return back to our days in trigonometry when we learned about sines and cosines, and in particular, the famous law of cosines. That's right. You've heard it here first. Well, not first, but again. Suppose that you have a triangle, and it doesn't have to be a right triangle, and the lengths of the sides are A, B, and C. The law of cosines actually is the generalization of the Pythagorean theorem that holds for any triangle, even when you're not right. Suppose that the angle between the sides A and B is given by theta. Okay? Then, in fact, what we see is that A squared plus B squared equals C squared, but there's a little bit we have to add. We have to add 2 times the length of A times the length of B times the cosine of the angle between them. Notice that when that angle is 90 degrees, cosine of 90 degrees is 0, so when it's 90 degrees, we get Pythagorean theorem. But if theta is not 90 degrees, then in fact, we still get this thing to hold with this extra term here. Now, how is this possibly of value to us? Well, let's take a look at this picture, but think vectors. So let's draw this picture now as a vector. So let's call this vector A. Let's call this vector B. Ooh, right up here. And then this thing right here is the difference of B minus the vector A. Okay, let's insert everything that we have here and see what this gives us. All right, this now is the length of the vector A squared. So that's the length of the vector A squared. That's this piece. Plus the length of the vector B squared equals the length of the vector B minus A squared, because that's what C is. See, that, if you take B and subtract off A, you get that exact vector. Plus 2 times the length of A, length of B, and cosine of the angle between them. Phew! Now that looks pretty complicated, but what can we do? Well, I can actually simplify that a little bit, and let me pull that out, because I've already said that if you take a vector and take its length and square it, it's the same thing as the dot product of this vector with itself. So in fact, we can use this. B minus A in length squared is equal to B minus A dotted with B minus A. And the dot product behaves like regular products in terms of the foiling, and so we can actually foil all this out. And when I foil this out, I get B dot B. And then my inside term is going to be negative A dot B, and my outside term is going to be a negative A dot B, and so I see negative 2A dot B. And then finally, a negative times a negative is a positive, and I have A dot A, and so I get plus A dot A. But wait a minute, B dot B, we've already said that that's equal to the length of B squared. And so if I write all of that in, these dot products begin to look a little familiar. Because that funny expression really equals this. Let's write that in right now. And so what I see here is this identity, the law of cosines, gives us the length of A squared plus the length of B squared equals this, which I see is the length of B squared minus 2 A dot B plus the length of A squared. That's all of that was just for this piece, so we're done with this. Boing. And then we've got plus 2 length of A, length of B, and I'm going to fit this in, cosine of theta. Well, look at this identity. I've got length of a squared here and length of a squared here. They cancel. Here I've got length of b squared here and length of b squared here. They cancel. I've got 0 on this side and these two terms on this side. Let's bring this over to the other side. It's a negative, so it becomes a positive. And so what I see is 2a dot b equals 2 length of a, length of b, cosine of theta. And the 2's cancel. And so what am I left with? I'm left with a dot b is equal to the length of a times the length of b times the cosine of the angle between them. Now, this is huge because now we see that the dot product is not some weird, wacky number, but it's connected with the angle between the two vectors. And so what does that mean? First of all, here is what we've just discovered. We've just discovered that a dot b is the length of a multiplied by the length of b times the cosine of the angle between them. And if I solve this for cosine, I see that the cosine of the angle between two vectors is equal to the dot product divided by the product of their lengths. Okay, so this is amazing, because what that means is if I'm given two vectors, A and B, I can actually compute information about the angle between them, because I know that the cosine of that angle is related to the lengths of the vectors and the dot product of the two vectors. So bottom line is the dot product of two vectors is connected to the angle between them. And in particular, it's connected via this identity, which followed from the law of cosines. So let's try an example. So first, we had no idea what, in fact, the dot product means, and now we see it's somehow connected to the angle between two vectors. So suppose I'm given this scenario right here. I've got a vector b and a vector a. They're given this by these coordinates. I want to find that angle between those two vectors. That means you imagine that vector and that vector sticking out. I want to know that angle between those two. If you think of the plane that contains both the vector b and a, I want to know the angle along that plane that's made by these two vectors. What do? Well, first I'll find the cosine of the angle. That's easy. That's just going to be the dot product divided by the length of the vectors. So I need the length of the vectors, and I need to figure out the dot product. So it's a lot of little calculations we have to do here, but not a big deal. I mean, let's just look at the length of this vector, for example. Well, the length of that vector, that's the length of the vector b. Oh, green. You should use green. It's just the square root of the sum of the squares of each of the components. So that's going to be 2 squared plus negative 2 squared plus 2 squared. And so that's going to be the square root of 8, 9, 10, 11, 12, which equals 2 square root of 3. So this length here, this length, is 2 square root of 3. And similarly, we could find the length of A, which I'll let you think about. It's just going to be the sum of the numbers 1, 25, and 49, then take the square root, and we see that this length is equal to 5 square root of 3. Great. Now, let's figure out the dot product. Well, the dot product we find with great ease, right? Because the dot product is a pretty easy thing. All we have to do is just multiply each of the corresponding components together and then add them up. And so what I see is that A dot B is equal to 2 times negative 1, which is negative 2, plus negative 2 times 5, which is negative 10, plus 2 times 7, which is 14. And so what do I see here? I see 14 minus 10 minus 2, which just gives me 2. So the dot product is 2, and we have the lengths to be 2 square root of 3 and 5 square root of 3. So the cosine of theta is equal to 2 divided by the product 5 square root of 3 times 2 square root of 3. And what does that equal? Well, the 2's actually cancel. And square root of 3 times square root of 3 is just 3. 3 times 5 is 15. And so I see this is 1/15. And so I see that cosine of theta equals 1/15. How do I figure out what theta is? Well, it's just the arc cosine. So theta equals arc cosine of 1/15, which we can approximate using a calculator. And I see, let me pull this over so you can see this. And so I can see this is about 1.5 if you're using radians. And if you want to use degrees, it's approximately 86 degrees. So the angle between these two vectors turns out to be 86 degrees, and you can see it was not that difficult to find using the dot product. So the dot product is heavily connected with the angle between two vectors. So now if we look at this expression and ask ourselves, what happens if in fact two vectors form a right angle between them? Well, then this angle is 90 degrees. And so what about their dot product? Well, their dot product will equal the length of A times the length of B times the cosine of 90 degrees. Well, the cosine of 90 degrees is 0. So here's a really neat thing about the dot product. If we have two non-zero vectors, then their dot product will be 0 if and only if those vectors are at right angles with each other. So the angle between them is 90 degrees. So that's a really cool way to see if two vectors are at a right angle or not. Sometimes we call two vectors that are at right angles orthogonal. Orthogonal vectors means that, in fact, we have right angle between them. So it's very easy to see if we have a right angle between two vectors, their dot product is 0. So there is a very powerful fact about the dot product, namely that we can tell if two vectors easily are at a right angle or not. We just compute this simple dot product, just taking the product of the corresponding components and adding them up. We get 0. We know the angle between them is a right angle. If we don't get 0, we know the angle between them is not a right angle, and we can actually compute what that is using this fantastic identity to get the cosine of the angle. So to summarize some of the fun properties of the dot product, let me just point out that it enjoys a lot of wonderful things. First of all, we've already seen that the dot product of a vector with itself is just the length of the vector squared, so that's a sort of cool one. Also, if you think about it, since we're just doing multiplication and addition of numbers when we actually compute a dot product, then A dot B is the same thing as B dot A, so it's commutative. The dot product is commutative. It also satisfies this distributive property. If you take A dotted with the sum of two vectors, it equals the sum of the dot products. Now, this is a little bit weird, because these plus signs are different. Do you see that? This is the plus of two vectors, so it's a vector sum. But a dot product is a number, and that's a number, and so this is usual addition of numbers. So these plus signs actually are different. In fact, maybe if we were really being careful, maybe I should make this a funny plus sign, because that's a plus of vectors, and this is a plus of numbers. Anyway, you get this sort of distributive property holding. Similarly, with scalar multiplication, if I take a look at the scalar c times the vector A and dot it with the vector B, it's the same thing as first taking the dot product and then doing a multiplication by c. Again, here, this is scalar multiplication, and this is good old-fashioned multiplication, because that's a number, and that's a number, and that's just regular multiplication. And finally, if you take the vector 0, 0 in all its entries, and you dot it with any vector, you get the number 0. And notice how this 0 has a little vector hat on it, because I'm thinking of it as the vector 0, the vector whose all coordinates are 0, and this is the number 0, because when you take 0 and add it up a bunch of times, you just get 0. So anyway, you get all these great properties holding, and the dot product is the key to figuring out angles between vectors. I'll see you soon.